In this lesson, we're going to introduce some of the fundamental concepts of mass spectrometry, covering some of the basics of how the technique works and what kind of data can be obtained from simple analyte molecules. Mass spectrometry is an analytical technique that measures masses of molecules and fragments of molecules. Mass spectrometry is performed in an instrument called a mass spectrometer. In a mass spectrometry experiment, analyte molecules are placed into a vacuum and then ionized. A very common technique for ionization is electron ionization. In this technique, the molecules are bombarded with a high energy electron beam, which displaces an electron to form a radical cation, essentially the original molecule minus an electron. The radical cations that are formed are then accelerated by attraction to a negatively charged grid and then pass through a magnetic field. As the radical cations travel, they are differentially deflected by the magnetic field based on each ion's mass to charge ratio. Particles with a lower mass and those with a higher charge will result in a greater deflection. Now, for typical organic molecules, the charge is always 1, and that means that the mass to charge ratio is going to be the same as the actual mass of the cation in AMU. The cations travel through the magnetic field and ultimately impact a detector, which can determine the mass of the particle based on the extent of deflection. The radical cation initially formed from the analyte molecule is called the molecular ion. In a low resolution mass spectrometry experiment, masses are measured with a rather low accuracy, sometimes as low as 1 AMU. In a low res experiment, the molecular ion's mass to charge ratio will be equal to the molecular weight of the original analyte molecule. And when you're trying to determine the structure of an analyte, knowing the molecular weight can be really useful. In high resolution mass spectrometry, masses are measured with very high accuracy, typically 1/10,000th of an AMU or better. And at first, this may not seem very useful, but if we dive into the details, you can see that this is actually extremely powerful. Because masses measured that accurately can actually be used to calculate a molecular formula, not just the molecular weight. So take a look at these two molecules. They each have a different formula. The first one, C7H8O, and the second one, C6H4O2. And in a low resolution experiment, they have the exact same molecular weight of 108. However, in a high res mass spec experiment, you can see that their masses are actually slightly different. The first one having a mass of 108.0575, and the second one having a mass of 108.0211. Now, what causes this difference in masses is simply because they have different formulas, and the different elements actually have slightly different masses when measured accurately enough. So here I've done the math. In the first molecule, which has 7 carbons, and a carbon 12 isotope weighs exactly 12.0000 AMU. It's actually what defines an AMU. And that means that the mass from those carbons is going to be 84 exactly, 84 AMU. The molecule then has 8 hydrogens, and again, if we assume the most common isotope of hydrogen, protium, has a mass of 1.0078, then we get 8.0624 AMU. And then finally, this molecule has 1 oxygen, and again, if we assume oxygen, the most common isotope is oxygen 16, that isotope has a mass of 15.9949. And when you add all those together, you get 108.0573. When you perform the same breakdown on the second molecule, you can see that because it is comprised of different numbers of different elements, the total sum is slightly different, coming in at 108.0210. And that means that if you do the math, or you have a computer program do the math for you, you can actually determine a formula from a mass that is measured accurately enough. And when you're trying to determine the structure of a molecule, knowing its actual formula is way more powerful than simply knowing its formula weight. Now, because the molecular ion is a radical cation, it's actually quite unstable. It's missing an electron. And typically, the molecular ion will undergo fragmentation to give multiple fragment ions. Now, the fragment ions, if they're charged, then they're going to be deflected by the magnetic field in the instrument and ultimately measured by the detector. A mass spectrum is a plot that shows the relative abundance and mass to charge ratios of each detected cation, both the molecular ion and all the fragment ions. The tallest peak is called the base peak and given a relative abundance of 100%. So this is what a typical mass spectrum looks like. You can see on the horizontal axis, we have the mass to charge ratio, And on the vertical axis, we have the relative abundance. So you can see that in this particular spectrum, we have what looks like four major peaks. Now, oftentimes, the major peaks will also have some much smaller satellite peaks. You can see that on the spectrum. And while some of those satellite peaks can occasionally be useful, we're going to just ignore them and stick to the major peaks in any given spectrum. So, how exactly does the molecular ion fragment? And why do we see differences in the relative abundance for the different cations? Well, in order to understand that, we need to know about the relative stabilities of different kinds of reactive intermediates. The three major forms of reactive intermediates are carbanions, carbocations, and radicals. Now, only two of these are actually pertinent to mass spectrometry, the carbocations and the radicals. But I think it's a good idea to go ahead and talk about all three at once. Let's start with carbanions. A carbanion is just a negatively charged carbon, and a negative carbon will always have a lone pair. For right now, the major stability trend that we're going to look at is related to the degree of substitution on the negative carbon. The higher the degree of substitution, the less stable the carbanion. So if you look at this generic representation of a carbanion, you can see that it's a negative carbon with three R groups attached to it. And again, R typically refers to an alkyl group, but in certain contexts can also represent really any group. So here we're using it to represent anything from a hydrogen through an alkyl group. So if all three of those R groups are hydrogens, that would mean you have a methyl anion, and that's the most stable carbanion possible. If all three of those R groups were some kind of an alkyl group, like a methyl group, that would make that a tertiary anion, and that is the least stable. And if you think about it, that should make some sense. Hydrogen has very little electron density on it, whereas an alkyl group, even something small like a methyl group, has a much larger electron cloud. And electrons repel other electrons, right? Like charges repel. And since the carbanion is negative, when you put other groups on there that have a lot of electron density on them, like alkyl groups, it tends to repel the electrons of the carbanion and destabilize it. So as you replace hydrogens with larger groups that have more electrons, it tends to destabilize the negative charge. Now, unlike carbanions, carbocation stability actually is important when looking at mass spectrometry. So here we have a generic representation of a carbocation. And a carbocation typically will have an empty orbital, an empty p orbital. Carbocations are electron deficient, and as such will actually follow the reverse in terms of stability trends from what we saw with carbanions. So with carbocations, the more highly substituted the carbocation is, the more stable it will be. So a tertiary carbocation, where these three R groups are all alkyl groups, will be the most stable, and a methyl carbocation, where these three R groups are hydrogens, will be the least stable. Now there are two explanations as to why carbocations have this particular stability trend. The first one I refer to as the electron tank model, and it's pretty straightforward. Again, hydrogen has very little electron density, has a very small electron cloud, compared to larger groups like alkyl groups. So as you replace the hydrogens on the carbocation with larger groups that have larger electron clouds, those electron clouds can be pulled in by the positive charge, thus stabilizing that charge. The second and more modern explanation is a bit more complicated, and it's called hyperconjugation. Hyperconjugation is kind of like a pi bonding effect. Every carbocation has an empty p orbital. And when you have alkyl groups right next door to that carbocation, the bonds, the sigma bonds that are attached to the adjacent atom, can actually line up almost parallel with that empty p orbital, creating a pseudo bonding interaction. Again, kind of like a pi bonding interaction, except now it is a sigma bonding pair of electrons in a neighboring bond that is overlapping somewhat with that empty p orbital. And because that is essentially an orbital overlap, it's very much like a bond, and so it has a stabilizing influence on the molecule. Lastly, we have radicals, and radicals are just atoms that have an unpaired electron. So a carbon radical is simply going to be a carbon that has an unpaired electron on it. Radicals and carbocations are both electron deficient species. A radical and a cation both will have an incomplete outer shell, an incomplete octet. Both will also have a p orbital associated with the electron deficient carbon. And that means that radicals will follow the exact same stability pattern that we saw for carbocations. The more highly substituted a radical is, the more stable it will be. So again, a tertiary radical will be the most stable, and a methyl radical very, very unstable. Now remember, in a mass spectrometry experiment, the analyte molecules are ionized into a radical cation, again called the molecular ion. Now because the molecular ion is a radical cation, when that radical cation fragments, it fragments into radicals and cations. Now radicals are not charged, and because they're not charged, they're not going to be deflected by the magnetic field in the instrument, and that means they're never going to reach the detector. But the cations that form during fragmentation will be deflected by the magnetic field and will hit the detector. And the more stable a fragment ion is, the more of it will be produced, the more of it will hit the detector, resulting in a higher relative abundance. And that means that generally, the taller a peak is on a mass spectrum, the more stable that particle is. So let's take a look at the fragmentation pathways of the simplest kind of organic molecules, alkanes. When an alkane is ionized into the molecular ion, it means that one of the valence electrons has been knocked away. Now, we don't know which one necessarily, but it does mean that one of the covalent bonds in the molecule is actually a bond made with only one electron. Since we don't really know where the electron came from, we typically represent the molecular ion for an alkane inside of brackets. We don't explicitly show where the positive charge is, nor where the unpaired electron is positioned. So here I show pentane being ionized from an electron ionization, and that results in a molecular ion with a mass to charge ratio of 72. And again, 72 is also the molecular weight of pentane. Now, in an alkane, because we don't know where that electron was knocked away from, technically any bond in the molecule can fragment. Well, there are only two kinds of bonds in an alkane, carbon-carbon bonds and carbon-hydrogen bonds. And we know that carbon-hydrogen bonds are much stronger than carbon-carbon bonds because they have a lot more S character. So cleavage of a carbon-hydrogen bond is a lot less likely to occur than cleavage of a C-C bond. And while CH bond cleavage does occur, it also doesn't really provide any useful information. So if you look at pentane, pentane has 4 carbon-carbon bonds, but it only has 2 unique carbon-carbon bonds. Because of the symmetry of the molecule, the outermost bonds are identical to one another, and sort of those inner 2 carbon-carbon bonds are also identical to one another. So let's take a look at what happens when fragmentation occurs along either of those 2 bonds. Here I've got them color-coded with a green line and a red line. So if that green dissection were to occur, think about what this means. We have a radical cation, and if fragmentation is occurring on this bond, that means that this bond is the one that only has 1 electron. So if this bond were to completely break, that 1 electron shared between those 2 carbons can end up sticking to either the left carbon or the right carbon in that bond after fragmentation. If the electron sticks with the left carbon, that's going to result in the formation of a methyl radical and a butyl cation. Now, the methyl radical is not charged, and because it's not charged, it will not be deflected by the magnetic field, which means it will never impact the detector. In other words, you're never going to see a methyl radical in a mass spec experiment. But the butyl cation is charged, and it will be deflected, and it has a mass of 57 AMU, and that means you should see a peak on the spectrum at 57 AMU. Now, with many fragment ions, it is very useful to represent the mass not only as the absolute value, 57 AMU in this case, but also in relative terms, relative to the mass of the molecular ion. So in this case, the mass of this particle is the mass of the molecular ion minus what fell off, which is a methyl group, which weighs 15. And that's why we can represent this fragment as M minus 15, the molecular ion weight minus 15 AMUs, the 15 AMUs that came from that methyl radical falling away. Now that same bond could have fragmented such that the electron ended up on the right carbon of the bond. That would result in the formation of a butyl radical, which again won't be observed, but it will also form a methyl cation. And again, because it's positively charged, that cation will be detected after deflection through the magnetic field. And of course, the methyl cation will have a mass to charge ratio of 15. And just as before, we could represent that mass as relative to the molecular ion mass. In this case, it would be from loss of a butyl radical, and a butyl radical weighs 57. So here we would have M minus 57. Now the bond dissected with the red line can fragment similarly. The electron that is in that bond can either end up on the left carbon of that bond or the right carbon. In this case, if the electron went to the left, it would result in an ethyl radical and a propyl cation. Again, you would only see the cation in the actual spectrum, and it weighs 43, or M minus 29, 29 being the mass of an ethyl radical. If that electron were to stick to the rightmost carbon of that bond, you would wind up losing a propyl radical and creating an ethyl cation, which would weigh 29, and again, in relative terms to the molecular ion, it would be M minus 43, 43 being the mass of a propyl radical. It is definitely worth learning the masses of some of these smaller alkyl fragments, methyl, ethyl, propyl, butyl, and pentyl, each having masses of 15, 29, 43, and 57 respectively. Actually, you can calculate the mass of a simple alkyl fragment simply by taking the number of carbons in the fragment, multiplying by 14, and then adding 1. So a methyl radical would have 1 carbon, so 1 times 14 is 14, plus 1 is 15. An ethyl radical that has 2 carbons, so 2 times 14 is 28, plus 1 is 29. So here's what a mass spectrum of pentane would actually look like. Typically the peak furthest to the right, that is the peak with the highest mass, not the peak with the highest relative abundance. That peak with the highest mass will usually be the molecular ion, and then all of the peaks with lighter mass will be fragment ions. So here you can see that the molecular ion has a mass of 72, which is the molecular weight of pentane. We can also see a peak at 57, and remember 57 is one of those masses you should remember. 57 is a butyl group. But we can also calculate that mass relative to the molecular ion mass. 72 minus 57 is 15, so that means that this is a peak at M minus 15. In other words, that peak tells me that this molecule has a methyl group that can fragment off. Next, we have this very tall peak at 43, and again 43, that's one of the numbers you should just remember, and that's a propyl peak. Again, subtracting that mass from the mass of the molecular ion would mean this is an M minus 29 peak. In other words, this peak came from loss of an ethyl radical. And then we have a peak mass to charge ratio of 29, that's going to be an ethyl cation, and again we could represent that as M minus 43, loss of a propyl radical. And then finally, we have a peak at 15. That represents a methyl carbocation. Again, we can represent it as M minus 57, loss of a butyl radical. And if you look at the relative abundances of a lot of these peaks, it should make a lot of sense. For example, the peak at 15 is really tiny because that represents a methyl cation. And a methyl cation is the most unstable kind of carbocation. So of course, very little of that will form. It's going to be a relatively small peak. The peak at 43, that represents a propyl cation. That's a primary cation, which, while not wildly stable, is still amongst the most stable cations that this molecule can form from fragmentation. So it's going to be a relatively strong peak. Now, it's often possible to actually make use of those differences in relative abundance. Let's take a look at the mass spectra of two related compounds, pentane and 2-methylbutane. These are actually constitutional isomers of one another. They have the same formula, C5H12. And of course, that means they're going to have the same molecular weight. So again, if you look at pentane, it only has two unique kinds of carbon-carbon bonds, so it only has two places that it can fragment. Each carbon-carbon bond can fragment in two directions, so you have 4 fragment ions and the original molecular ion, so you should have 5 peaks on the spectrum. If you look at 2-methylbutane, it actually has 3 unique carbon-carbon bonds. However, cleaving any of those 3 bonds results in fragment ions that have the exact same masses we saw for pentane. Now, if you look at the two spectra very carefully, you can see one big difference, and that is the peak at 57 for the 2-methylbutane is much more intense than the same peak in the pentane spectrum. Now, 57 represents an M minus 15 peak, right? That is from loss of methyl. Now, when pentane loses a methyl radical, it would form a primary butyl cation. But when we look at 2-methylbutane, 2-methylbutane can actually lose a methyl radical in a couple of different ways. But most importantly, fragmentation of this bond would form a secondary cation. And a secondary cation is more stable than a primary cation, which means more of those cations will form, more of them will hit the detector, giving rise to a taller peak. So given these two spectra, if you know that you have these two isomers, you could actually determine which compound belonged to which spectrum, simply by understanding the fragmentation patterns of alkanes and applying the knowledge of these relative stabilities of carbocations. Because 2-methylbutane can form a secondary carbocation by loss of a methyl radical, it's going to give a taller peak at 57, at M-15, than would pentane.